All right, so now let's try a second example. In this case, all that I changed from the first example is I wrote a 0 here. It used to be 5, 1, 1, 5, now it's 5, 0, 1, 5. What we'll see is it changes the eigenvectors and eigenvalues both. So the first thing we might want to do is we might want to calculate the eigenvalues. Well, this 0 here is going to make the determinant pretty simple. Again, we use the determinant of a minus lambda I, and a minus lambda I is 5 minus lambda, 5 minus lambda, 0, and 1. And its determinant is equal to 5 minus lambda squared. And setting that determinant equal to 0 is pretty trivial. We just want lambda to be equal to 5. But it's not just once, right? We see this squared. So this is 0 squared. It's extra 0, 0 times 0. What we're looking at is the root 5 having a algebraic multiplicity of 2, meaning it appears twice. It's a double root. There must be one vector for the eigenvalue 5. Is there just one, or are there two? Only one way to find out, and that's to just try to find them. I'm going to use that a minus lambda I matrix times x is equal to 0 formulation, that second formulation from the first example. So let's take this with our eigenvalue being equal to 5. And what we'll see is that that makes this matrix 0, 0, 1, 0. I'm going to say that times x1, x2 is equal to 0 and 0. And let's look at this first line. Let's look at this as a system of equations. The first one says 0 plus 0 is equal to 0. That's manifestly true, but it's not terribly helpful to us. The second one says x1 plus 0 is equal to 0. So in this case, what we're really saying here is just that x1 is equal to 0. Okay, well, it's pretty easy to think of vectors where the first element is 0. So let's have v1 be, for example, 0, 1. And if you take that and you multiply a by that, you will get 0, 5, which is 5 times v1. That's what we wanted. So we did find an eigenvector. But now the fun begins. I want you to try to find me another vector that also satisfies this equation, that is not just a scaled copy of v1. It's not just some constant times v1. At the end of the day, you won't be able to. The only constraint that we have is x1 is equal to 0. Turns out once you have x1 equal to 0, we're talking about a line, the vertical line, if you use the usual two-dimensional representation. There aren't two different vectors on that line that aren't scaled copies of each other. Everything is 0, 1 times something. So there's actually just this one vector. There's just v1. So this matrix is what we call defective. It only has one eigenvector associated with the eigenvalue 5. That's this eigenvector. There is no other eigenvector that is associated with that value. If you wanted to be complete about that, you could write some kind of proof where you'd say, well, let's suppose there's some v2 that also satisfies this condition. So you might say, for example, v2, well, that first element's got to be 0, but let's say that the second element is something like k. It's some constant, something that we don't know yet. And you would say, is v2, is that equal to some other constant, let's call that k2, times v1? Because if it is, it's just a scaled copy, and obviously k2 is equal to k, and you get the relationship that these two things are the same. So we don't really have a second vector. That's just a made-up thing that we tried and didn't work out.